Okay. So this course, I want to cater it a bit differently. It's a pretty interesting course, but you do see that in the syllabus, there are a lot of repetitions with the other parts of the other units, right? So you're like, why is it repeated here again? Okay. So the main idea of this course is to actually get you to merge the two concepts that you've learned before. So you want to merge the numerical techniques and you want to merge the idea that you have about basic physics problems. Okay, so you merge them together and then you get certain results out of them. Okay, so let's just, okay, so before I go on to actually explain about the entire course, I will tell you there's going to be a little bit of grading system. Okay, and this grading is something that I want to know. There's going to be I want to know if I'm able to convey to you what I need to convey to you. And also you will be able to know if you've actually taken something out of the course. Okay. So there are going to be polls in between the classes. I'm just keeping you informed about it. We will go ahead. I will explain to you there are the methods that we're going to be using. We're going to have polls. We're also going to have a Google form at the end of the session. So it's going to be in class tests and after class tests, which is probably going to be around 5 minutes or so, and you can finish it off pretty quickly. Okay. Yeah, so first things first, do not try to switch on your mic and play music and stuff. Okay, so I don't like that. I don't like getting interrupted, and there's a lot of effort that's played over here to do this entire thing in a very good way. Okay, do not post unnecessary messages. This happened a lot of time last year. Okay, do not try and insult your other classmates in the chat box. This actually happened. That's why I'm putting that down here. Okay, now all questions to be addressed at the end of the class. So if you do have any questions with the material, if you do have any questions with the references, etc., you will wait till the end of the class. Or if you think you're going to forget the question that you thought of, you will type it down in the chat and you will message it to me. Okay, and I will address them again at the end of the class. Okay, because interrupting myself and taking that question up in the middle again in an online platform is going to be very hard. Now, if you can, you mentioned the slide numbers. So if you do see this part, okay, so you see this 2 out of 30 slides or whatever, you do mention the slide number so I can go to that particular slide. Even if it is a question that you just thought of and it's not really relevant to the content, let me know at what point or what slide number you actually thought of that question. Okay, and like I told you, there are going to be in-class and after-class tests. Will this be accounted for your internal assessment? No, but this will be accounted for your attendance. Okay, so the way I will mark your attendance is 1, through polls. Okay, so if you answer the polls, I know that you're present in class. 2, I will use Google Forms. Okay, so after the class gets over, immediately I will post that in the chat. Okay, if you do have issues, this is the first class that we're doing. If you do have any issues with accessing the Google Forms, you will let me know. Okay, there are, I think a couple of you guys have my number, so you will let me know if you have issues accessing the Google form. Now the Google form will be live only for a short period of time of about 10 to 15 minutes. Okay, it does not take more time than that to fill in the form and submit it. These are questions that you have. These are actually tests. Okay, so you fill in that and you let me know. It will be based on the class. Okay, so it will be based on the class that we have. So you fill in that and you submit it. After about half an hour or 1 hour, I'll reveal your responses. So you'll get the test score that you have. Okay, so I think you should really take this seriously, even though it is not accounted for your internal assessment directly. It was accounted for your attendance, and your attendance accounts for a certain amount of marks, right? So you will try and attend them. Okay, so I realized that last class we had about 61 participants and now it's 44. Okay, so you think that you're not going to be, marked your attendance? No, I will get all the details from all of you people. Okay. Next, okay, so I want to know if you can really understand how polling works. So I'm going to be putting a test poll right now. Okay, so you will be answering those questions to me. Okay, so I will start this poll. I will launch this poll, and you will start clicking in the options that are there. Okay, so the first question is that are you alive? Okay, so you have to answer yes or no. Okay, so it's a very simple question. It's just to get the idea of have you understood how polling works. Okay, so I will launch that right now. Okay, and I hope you've seen something on your screen, so you will enter the answers around that. Okay, so yeah, I'm getting a lot of replies. Okay. God forbid you people enter no. It's gonna be funny if you people enter no. Okay. You do know that this accounts for your attendance, so you will mark them, okay? Okay. Okay, so 33 of you guys answered, and there's 46. Okay, I've got a question in the chat. That's not the way our attendance works. You answer to the poll if you can. Okay. Okay. Right. Okay, so let's stop the polling. Okay, so I get to share the results with you people. Okay, so there are about 45 participants and 33 of you answered yes. Okay, so let's go to the sections. Okay, so let's go to the actual sections that are there in the unit. Okay, so the first part that you have is I'm dividing this into 4 sections so that it's much more easier for you to understand. So the first section that you have is application of numerical differentiation. The second section that you have is to approximate integrals. Okay, so this is a technique that is used to approximate integrals. The third section that you have is to find Legendre polynomials using recurrence relations, and recursion relations that you've actually computed these recursion relations in your first semester. Okay, so you've worked about the Legendre differential equation, the Legendre polynomials, and yeah, and using all these recursion relations and stuff. Okay, so the next section that you have is finding energy eigenvalues. And how are you going to be doing these? How are you going to be finding these energy eigenvalues? You're going to be using the basic methods that you know to find roots. And what are those? Your bisection method and your Newton-Raphson method, and you're going to be using those. Okay, so let's move on to this. Okay, so like I said before, the idea behind the course is to integrate these 2 concepts of numerical techniques and your physics problems, and then you get useful results out of them. Okay, so what are we having to look at? What are the physics problems that we look at? We look at Newton's law of cooling, we look at freely falling body, we look at falling body with air resistance. Okay, and we would be using these 2 techniques because all of these that you see, okay, are basically represented using differential equations. Okay, all these physical problems that you see are modeled using differential equations. And what are the methods that you use to actually calculate actually compute the solution for the differential equation? You use Euler's methods and Runge Kutta methods, so that you can calculate the numerical solution. Okay, it's not necessary that all the time that you're able to calculate the explicit solution of the differential equations. Okay, there can be circumstances where you cannot get the solution to the differential equation. Therefore, you use numerical techniques or numerical methods to calculate the solution to the differential equation. Okay, so it's better because then you're able to use a computer, and all you have to do is repeat the whole process. Now, this course should be actually accompanied with programming, but that's not the way it is done in BU syllabus. Okay, so what we will do is we will actually be the computer, and we will actually calculate this step by step. Okay, so we will have a problem and we will actually calculate it step by step. Okay, now, okay, so let's just go on to this. Okay, why differential equations? Okay, it tells you how basically a system evolves in time. Okay, how does not just time, but rather any other parameter. Okay, so it tells you how to model or simulate a system. Now you notice that if you take Newton's laws of motion, you have differential equations there. Okay, If you take the Schrodinger equations, you have differential equations there. Okay, so from big to small, all these things are basically governed by differential equations. Okay, so from Newton's second law to the Schrodinger equation, almost every system that you look at, big or classical, to small or quantum, okay, is associated with differential equations. Now, what are differential equations? You do not realize the subtleties of actually working through this. Okay, the reason that differential equations are special is because you have the derivatives of the function associated with the function. Okay, unlike an algebraic equation, let's say where you have say when you're looking at an algebraic equation, you have an x squared plus 2x plus 3 is equal to 0, whereas in your differential equation, what you do have is that you have, let's say, dy by dx, or let's just write e squared y by dx squared here, and let's just write 1 here. Okay, let's say is equal to y. Okay, so you have the derivatives of the function, okay, say y, associated with the function itself. Okay, so just a second. So the waiting room is disabled. Everybody can enter. Nobody's in the waiting room. So the waiting room has been disabled. Anybody can enter at any time. Okay. Yeah, so this is what you have here. Okay, so the difference between these differential equations and the algebraic equations that we have. Okay, so you relate a function with one or more of its derivatives. Okay, now what I'm going to do is I'm going to put up a poll. Okay, to let's see, understand how much you know. Okay, so let's start off this poll. Okay, I'll just read the question before we start off the poll. So what is the solution of a differential equation? Is it a number? Is it a number or a set of numbers? A function or a set of functions? Okay, and the second question that you have is true or false. The Schrodinger equation is not the quantum counterpart of Newton's second law in classical mechanics. Okay, so you answer the questions, you think carefully, because I just explained the difference between your algebraic equation. So you think about the solution of an algebraic equation that comes up. Okay, you also think about the solution of a differential equation. We've been working with this since probably 3 or 4 years now, right? We've been working on this since our bachelor's degree. So you think about that, and then you come up with the answers. Okay, so attendance will be marked irrespective of your answer is wrong or right, but I want to know how much you guys know. Okay, so I will start the poll now. Okay, I was sharing results, is it? Okay, it's fine. I will start the poll now. Okay, so you put in your answers there. Okay, so one person has answered. Okay. 10 people have answered. Okay, so 28 of you guys have answered. Should I wait for more time or should I end the poll? Okay, so there are answers coming in. Okay, 36 people have answered. Can I get it up to 48? Okay. So, yeah, so I think the number is standing stagnant. Okay, there's somebody else entering the answer. Aha. Okay, so I'm going to be ending the poll now. Okay. Okay, the poll has been ended. So, okay, so let me share your results and let's discuss what's wrong here. Okay. So what is the solution of a differential equation? And the majority of you guys answered a function. Okay. So is it just a function or is it a set of functions? So when you solve your differential equations, or even if you try to, let's say, look at the harmonic oscillator's differential equation, right? Differential equation used for the harmonic oscillator problem, you can have different functions associated with that. You can have a sine or a cosine function, okay, which is going to give you the solution, right? So you can have a function or a set of functions, okay? So if you try a simple differential equation, let's say, let me just annotate here, okay? So I will just write this down. Okay, so if you have a simple differential equation like d squared, okay, so let's not put squared there. Okay, so we have a dy by dx, okay, and equal to y. Okay, so let's say you have an e power x. Okay, so when you take dy by dx, what you do get is e power x again. Okay, so if y is equal to e power x, this is what you get. Now, is there another solution that you can put into this whole thing? Okay, so let's look at a different function. Let's say, what can we say? We can say, okay, so why don't you do this thing? Okay, so why don't you get back to me on this and let's look at what other functions satisfy this differential equation. Okay, so if you do find something right now, you let me know in the chat. Okay, so let's look at a different kind of a function that can be associated with this differential equation. Okay, so you do let me know that in the chat if you can find one. Okay, so otherwise we'll come back to it later on. Now, so the answer is this. Okay, so the answer is a function or a set of functions. Okay, the next thing that you have is true or false. The Schrodinger equation is not the quantum counterpart of the Newton's second law in classical mechanics. Okay, so the Schrodinger equation is not. Okay, the Schrodinger equation is the quantum counterpart of the Newton's second law in classical mechanics. Okay, so basically, when you're looking at your Newton's second law of motion, the trajectory is going to tell you, the trajectory is going to be governed, and then you write it as a function of time, right? So like that, the Schrodinger equation, you write it as the evolution of the wave function, right? So you write it as the evolution of the wave function in time. That's the solution that you're going to be getting when you look at the Schrodinger equation. So it is the quantum counterpart of Newton's second law of motion. Okay, this is actually false. Okay, so in majority of you answered true. Okay, and possibly that is because you did not see the word not. Okay, so be very careful about that. Okay, so I will stop sharing the results. Okay, and let's clear all of this. Let's go to the next part. Okay, so let me just check the time. Okay, so yeah, okay, so let's consider this simple first order differential equation. Okay, so we're doing a review of your ordinary differential equation. Dy by dx is equal to f of x comma y. Okay, to solve this equation numerically, what do you need to do? You need to discretize the differences that you have. Okay, we need to convert the differential equation to a finite differences equation. Okay, so what do? This dy by dx, you would write it as a delta y by capital delta y by delta x. Okay, you would try to discretize the whole thing so that you're able to solve it. Okay, so if you make it into small chops of pieces, okay, you're able to kind of like simulate a continuity, even though it's not continuous. Okay, now what is the simplest solution that you can use? You can use Euler's method. Okay, and now we will go on to understanding how Euler's method works. Okay, so in the questions that you get, okay, they won't give you the values that you have. So in your final exams, what happens is they won't give you the values, they'll give you very general question. they will tell you to solve the Newton's laws of equation numerically. I mean, so to solve the Newton's law of cooling, which we will be discussing now, numerically. Okay, so that's what they're going to give you, and they won't give you the values, or they won't give you the starting point or the initial points, and you're supposed to build on that on your own. Okay, so you have this. Okay, so suppose we'll start off with the basic part of Euler's equation, Euler's method. Okay, so suppose that you have a point, let's say x naught, where the function has a value y naught. This is something that you've done a million times probably this course. Okay, and we want to find out the approximate value of y in a point x1 which is close to x naught. Okay, so you say, okay, fine, I have a point x naught, I will increment it by a small delta x, and then I will get x1. Okay, so now what do? You're going to discretize these differences, right? So then you have your dx, which is your delta x, you have your dy, which is your delta y, and then you have x1 minus x naught, which is going to be giving you a delta x, that small portion, and you have a delta y. So you're going to have to take the y1, the function itself, and then subtract it from the initial points that you used. Okay, fine. Now all's well. Okay, so we try to discretize the differences, and now we're going to go on to evaluating y1. We're going to evaluate the next value of the function. Okay, so what is the idea here basically? So the idea here is, let me just draw that graphically for you. You have, let's say, a function f of x comma y. Okay, or let's just put this as y. Okay, let's just stick on to single variables, and you have an x. Okay, so you have some kind of a function here. Okay, so you're given a point at x naught, you find out your value, let's say at y naught. Okay, this is the initial condition that's given to you, and then you increment this guy by little amount. Okay, very little amount. Okay, not too much. Okay, because then you don't get the point at all. You increment this guy by very little amount, and then you get something like this. Okay, so you have a y1 and you have an x1. Okay, so at this point x1, you calculate what your y1 is. Okay, so that's basically the whole idea behind your Euler's method. Okay, so let's go on to this. Okay, so what do? We approximate the value of the function. Okay, so you're going to be approximating this based on the slope value that you get. Okay, so what are we writing this f of x naught y naught as? That is actually the function itself. Okay, that is actually the slope itself, right? So what did we have in our differential equation? We had dy by dx is equal to some kind of an f of x comma y. So this guy is basically the slope, and this guy is your interval or your increment that you have for x. Okay, so you know everything, and you can get the next value out. Now, why is this very easy? Okay, this is easy because you can just repeat it or put it in a loop, and the computer will give out your answer. You don't have to actually put any effort to this whole thing. Okay, so let's go to the next part. Okay, now, like I said, we generalize this whole thing. So if you want to find out y2, you use the y1 and x1 points. Okay, so y2 is equal to y1 plus f of x1 comma y1, which is the slope at x1 comma y1 into the increment delta x. Now, generally, what can you write? You can write yn plus 1 is equal to yn plus f of xn comma yn, and then you have delta x. Okay, so this is pretty simple. Now, the question to you will be to evaluate Newton's law of cooling numerically. Okay, and if it's, God forbid, if it's for 10 marks, what you're going to do is you're going to have to do this whole thing for the Newton's law of cooling differential equation. Okay, so the differential equation governing Newton's law. Okay, so now this is good. This is all fine and well and good as long as your delta x is small. Okay, and another thing that you have to be very careful about is the value or behavior of the function itself. Okay, so you need to have two requirements to understand what these values, this function is going to look like. Okay, so you have your f of x. One of the criteria is that it has to behave smoothly, and the other one, it must not have rapid variations. Okay, you can't have a very, very rapidly oscillating function. Okay, it has to have some amount of behavior associated with it. Okay, so yeah, okay, so what you have to notice is that, okay, you want you want to go and look at the Taylor's expansion once your class is over. Okay. And the funny thing that you realize is the Euler's method is basically the first order Taylor's expansion. Okay. It's almost equivalent to the first order Taylor's expansion. Okay. So you'd have x minus a. Okay. Probably you would have done it with a, and that would be your interval that you have here, your delta x. Okay. Now, what I want to talk about is I want to talk about errors. Okay, next. So there is going to be something called the global and local errors that are going to be associated with while you're doing your program. So there's a local error in calculating your x1. Okay, so that is going to be of the order of, in this particular scenario, it's going to be the order of x squared. Why is that? Because if you look at the third expansion, the Taylor's expansion, you will have an x minus a whole square, and then you have an f double prime, right? So you're going to have the local error that's associated with calculating, say, a point x1 as delta x squared, because we're trying to do an approximation. It's not the exact value as that of the function. We are doing an approximation, right? We're approximating it to by extrapolating the slope. Okay, that's what we're doing here. Now, if we use this method n times, because we're doing computational techniques, right? So we're trying to do this reiterative process. So how many times will you do it? Say you do it for n times the order of that particular error that you get for one iteration will be equivalent to order of delta x. Okay, so this will be your global error. Okay, so that would be the propagated global error. Okay, so the reason why we're interested in this is because we want to know how feasible this method really works. Okay, is how feasible or how much of an approximation can you make? Okay, how much of an approximation is bearable? So local truncation error is basically for one iteration, whereas global truncation error is for, say, the entire problem. Okay, so the amount of truncation error that you got to solve the entire problem. Okay, so those are the two types of error that you can come across in these kind of methods. Okay, so now let's come on to Newton's law of cooling. Okay, so we know this. We've been probably since high school. We've been looking at this particular thing. Okay, so Newton's law of cooling has been taught ever since high school. Now, what does it tell you? It tells you if the temperature difference between an object and its surroundings is small, then the rate of change of temperature of the object is proportional to the temperature difference. Okay, so capital T is basically your temperature, small t is your time. T refers to the temperature of the object. Okay, T refers to the temperature of the object. Ts is your temperature of the surroundings. So get that into your head. Okay, so T is the temperature of the body, Ts is the temperature of the environment, R is your cooling constant, and it depends on the following. Okay, so there are three things that it depends on. One of it is the heat transfer mechanism. Then you have a contact area with the environment, so it depends on your contact area as well. And the last thing that it depends on is the thermal properties of the body itself. Okay, so this is what you have as a summary of Newton's law of cooling. Your idea is not to derive Newton's law of cooling. Let me make that very clear. You're not going to be deriving Newton's law of cooling. Rather, you're going to use Euler's method to work on Newton's law of cooling. So you will take that differential equation and you will write it like we wrote it for the dy by dx is equal to f of x comma y. Okay. So you're not going to go back to high school and derive Newton's law of cooling. Rather, you're going to be using Euler's techniques and not deriving exactly, you're going to be solving numerically Newton's law of cooling. Okay, that's the whole difference between this. Okay, so what does the negative sign tell you? The negative sign, so let's say the temperature of the body is greater than the temperature of the surroundings. So that means there is a natural cooling process that is involved. Therefore, you need a negative sign along with the differential equation. Okay, if you've noticed, okay, so how does the curve look like? Okay, so you must have seen this. The curve basically looks like this. Okay, so you have temperature on one side and you have time on the other. Okay, so that's how the curve looks like. Okay, and we will look into the explicit solution of this this differential equation that we have for governing Newton's law of cooling. Okay, so let's look at this. Now, the idea is to use, like I told you, again, I'm repeating this over and over again because it's very confusing when you just have topics that are mentioned to you and you do not have a trajectory in which way to go to. The idea is to use the Euler's equation to calculate the temperature of a body at a given time t. Okay, and then given your cooling constant, you're able to calculate and this temperature at the time, initial time, your initial condition. Given the initial conditions, you calculate it at a later time. Okay. Now let's go on to the problem. Okay, so the problem is, what is the temperature of a body at a time t equal to 3 minutes when the temperature at t equal to 0 minutes is 83 degrees C? Okay, so the temperature of the surrounding here is given to be 25 degrees C. Okay, so temperature of the surrounding is given to you. The initial temperature of the body is given to you at the initial time t equal to 0, and the cooling constant is given to you. So everything is given to you, and you've been told to calculate it for different intervals. Okay, delta t is equal to 0.5 and delta t is equal to 1.0, and you need to compare with the exact analytic results. Okay, so we will be doing it analytically, which will tell you what kind of a form this whole Newton's law of cooling looks like. Okay, so it will tell you the form of Newton's law of cooling, and then there are questions based on that. Okay, so not here, but in your Google form, there's going to be a question based on the curve. Okay, how the curve looks like. Okay, so the formula is given to be dt divided by dt, which is equal to minus r, capital T minus capital T s. Okay, and we know all of this. Okay, we know all of that. Now, what do you do? Okay, so what was given to you? The temperature of the surrounding was 25. Okay, the cooling constant was 0.1 per minute. Okay, it gets cancelled off, so you understand where the per minute and when you kind of like look at the LHS and RHS, the units kind of match, so you get the idea that the cooling constant has to be per minute. Okay, and you have a function of time comma temperature. Okay, so capital T is temperature, little t is time. Okay, so you need to be able to solve this using your Euler's technique. So at time t is equal to 0, okay, what is the temperature? T naught, that is of the object, you have 83 degrees C. Okay, so we didn't really derive, but we looked at the form of the Euler's method, right? So you had yn plus 1 is equal to yn plus f of xn comma yn into your delta x. So that's what you have here. So delta x, you're changing the time by, say, 0.1 or 1, okay? And that's your interval that you change it by, and then you substitute this, okay? So this, you should have done a lot of problems on this in your numerical methods class in your second semester. Okay, so now there is a quick and easy way to calculate this in your calculator. Okay, so instead of, okay, so in your calculator, what you basically have is you have the option for answer, right? So what you do here is, let's say you type out 83 and you say equals. So your answer is stored as this particular value, okay, 83. So you have answer plus this function that you had was negative 0.1, okay, and you had t minus 25, right? That was your surrounding. So this guy is going to be answer again, because that's the initial value of the temperature, right? So you have an answer here, okay? And then you have this delta t increment, and they've given the step size as 1 minute. Okay, so you end up writing 1 minute. So in your calculator, how is this going to look like? You have an answer plus minus 0.1, answer minus 25. This is because the differential equation is so simple that you can incorporate the function into the whole thing as well. Okay, and then you would have 0.1. Okay, so you just have to keep pressing equal to over and over again. So how many ever iterations that you want, and you keep getting these values. Okay, so yeah, I think this is like a pretty quick method to do it rather than sit and compute it yourself. So if you have the calculator, then this is a very good thing. Okay, so you're basically doing the job of a computer there. Okay, so what the computer actually does, it does not take in, it basically takes in your answer value and then puts it back over and over again. So you're putting it into a loop, and that's how you write the program. And I'm sure you've written a program for this in C. Okay, so that is the idea. Now, where does the issue come? The issue comes when in the question, they're not going to give you these values. Okay, so you're going to have to remember these values, or you're going to have to make it up yourself on spot. Okay, so that's where the issue comes. And I'll show you some of the questions that they've given in the previous papers. Okay, a collection of those questions. Okay, So let's move to the next slide. Okay, so this is for your delta t is equal to 0.5. Now, what do you have to change? All you have to do is you had an answer plus your minus 0.1 into your answer minus 25 into instead of 1 minute, what you have here is a 0.5 minute interval. Okay, and you just have to keep pressing equal to and you will get all of this stuff. And I'm sure some of you might know this technique, some of you might not. So yeah, it's a very good way to save time. It's a very efficient way to save time. Okay, so now let's compare these two intervals that we have. Okay, before that, let's look at the analytic solution. Okay, so the analytic solution is very important because there's a question that's based on this in your Google Forms. So you'll have to be a little more, you need to think of it. Okay, because I'm showing you the answer and it's not very explicit in the form. Okay, so this is the given ordinary differential equation that you have. dt divided by d is equal to minus 0.1 t minus 25. And what do? It's a very simple differential equation. So you use the variable separable method. You put all the t's on one side, capital T's on one side, and you put all the small t's on the other side. And you integrate this. Okay, so when you integrate 1 divided by minus t plus 25, you get a negative sign because of this. Okay, because of this minus t that you have here. And you get a ln of t minus 25, which is equal to t plus c1. And then where you basically have your C1 as your arbitrary constant. So you need to calculate your arbitrary constant. Okay. Now, how do you write this? Basically, this is e to the power of this guy is equal to what you have here. Okay. So you take this guy down. Okay. You take minus 10 down. And then you have e to the power of this term. That is 1 by 10 minus t minus C1 plus 25. Okay. So what have you done? You've taken this negative sign and this 10 down. Okay. And so you have this. Okay, so that's the explicit solution that we have. We want to calculate the arbitrary constants now. So you want to calculate the arbitrary constants. What do? You put in the initial conditions, right? So you put in the initial values at t equal to 0. You had 83. So you finally be able to calculate the constant. This is a very simple manipulation. Okay, algebraic manipulations. And then you substitute it back into the equation. So this is the final equation that you get. You have no more constants. All you have is temperature that is dependent on time. So you get this. Okay. So this is a very, very easy method. I want you to be careful about this. This is an exponential. Okay. So this is what kind of an exponential? It's a decaying exponential, right? That's why you have your cooling curve to be this way. Okay. So what do we get at t equal to 3 minutes? Okay. So at t equal to 3 minutes, we have 67.975. All you have to do is plug in these values, plug in the value of t over here. And that's all you have to do. So let's just go back. Okay, so let me just write this down so that we don't mess this up. You had 67.9674 at t equal to 3 minutes. Okay, so let's go back. Yeah, okay, so where do we have our time? Here we have this. So you have 67.63533 over here. And this is quite close to what we have here, okay, from the actual solution, from the analytic solution, not the numerical one, but the analytic one. You have 67.282. So you do realize that as you decrease the size of the interval, as you decrease the step size, the value gets better and better. So this is something that you know. I hope you remember. Okay. Yeah, so we're done with this part. Okay, so let me just show you how the solution looks. Okay, so this is basically the purple curve is your analytic solution, and you've got the points that's like really crowded up in this region. So let me just expand that and show you how it looks. So the blue dots are basically the points where you had your delta t equal to 1 minute. Okay, and the red dots are the points where you had a step size of 0.5. Okay, so the red dots are the ones where you had a step size of 0.5. And if you look at it very closely, you can see that it's quite close to the analytic solution when you look at the red dots. Okay, so as you increase the step size, as you decrease the step size, you get values that are closer and closer to the analytic solution. Okay. So let's start off with another pole. Okay, so the Euler's method is equivalent to a first order Taylor's expansion about the initial point, true or false. And the Euler's method rests on the idea that the slope at the points can be used to extrapolate the next. Okay, so at dash number of points. So what are the number of points that you have here? Okay, so let me just repeat that again if it's not very clear. Euler's method is equivalent to a first order Taylor's expansion about the initial point. This is a true or false question. And the other one that you have is Euler's method rests on the idea that the slope at dash point or points can be used to extrapolate the next. Okay, so we're starting the poll now. Okay. Okay, why aren't you guys voting? Ten of you guys have voted. Thirty-one of you people. I will wait for 40 seconds and then I will close the poll. Okay, we're running out of time. Twenty seconds left. Ten seconds left. Okay, so I'm stopping the polling now. Okay, so I will share the results with you. Okay, so let's look at this. The Euler's method is equivalent to a first order Taylor's expansion. Okay, so majority of you answered true. I'm happy with that. Two of you answered false. You weren't listening, okay, because this was something that was mentioned in the slide in bold. Okay, so you have to pay attention. Okay, so that's a key in doing well in your polling results. Okay, so you have to pay attention. This was mentioned in bold on one of the slides. The Euler's method is equivalent to a first order Taylor's expansion. And I actually told you we should go ahead, you guys should go home, look at the Taylor's expansion and look at the Euler's method answer and kind of like compare and look at it. Okay. The next point, and I'm quite surprised at this, okay, because you guys have learned Euler's techniques, okay, Euler's method, and you've actually done a program on this, okay. So let's look at what went wrong here. Euler's method rests on the idea that the slope at dash point or points, okay, this was very tricky because I wrote points down here, okay, in bracket S. You probably thought it's 2. Maybe, I don't know. Okay, so the Euler's method rests on the idea that the slope at dash point can be used to extrapolate the next. I hope you remember your Runge Kutta methods because we're going to be using that here. Okay, so when you have your Euler's method, how many slopes have you used there in that equation? Okay, so you've just used one of them. Okay, so you've just done one of them, right? So it is at a particular point, at just one point where you evaluated the slope and extrapolated that particular slope. Okay, so it's only one. The answer is 1, not 2, which 20 of you answered. Quite surprisingly, 20 of you answered, but it's actually 1. Okay, for the 8 of you who answered. So I actually know who's answered what. So be aware about that because that is going to be added to your grade that I'm going to give you for the particular class. And then the next class, I would be listing these names out. Okay, so probably not this class. I'm going to be a little bit lenient, but next class onwards, I'm going to be listing the names out for those who have actually done well. Okay. Okay, so I'll stop sharing the results and let's go back to this. Okay, so I will share all these previous year questions with you. Okay, so this is compiled from all the other universities as well. Okay, so the VCU, BNU, and all that stuff. Okay, so solve the equation for the Newton's law of cooling using the Euler method. Okay, so they are actually asking you to, basically what you have to do is replace all the y and the x by capital T and small t. Okay, so that's sorry, the x and the y by capital T and small t. Okay, so that's what you have to do in this particular question. State Newton's law of cooling and solve numerically. Okay, so if this is a 5-mark question, you have to be a little more, you can't just go ahead and solve the entire problem. But if you're quick enough, yeah, go ahead and do that. If you're not quick enough, you have to kind of like improvise and just put the first section that we discussed on Euler's technique in the form of T and little t, capital T and little t. Okay. And then the next one, I think this is a 10-mark question. Explain the application of the technique of numerical differentiation for solving the governing differential equation of Newton's law of cooling. That means you have to do everything. Okay, so you have to do everything. You have to do everything, and then yeah, you'll have to do the problem as well. So you do the initial description of your Euler's equation, you write down Newton's law of cooling, and then you solve the problem. Okay, so the problem, you have to have it in your head. Okay, you need to be able to manipulate and get values out on your own. Okay, so these are not complete questions. These are questions that are going to help you improvise and write it down. So basically the idea is to not let the best student get marks, okay, and to not let the weakest student lose marks. Okay, so that's the idea that they frame when they set this question up. Okay. Okay, so now what I'm going to do is we discussed about one of the physical problems, right? We discussed about Newton's law of cooling. What your homework is to use the Runge Kutta methods and solve the same problem. Okay, so I will put a homework slide. There is a homework slide in the presentation. So the formula that I'm going to be giving you, okay, I will be sending all of these things down. Once you do the Google Forms, your email IDs will be registered. So I will be sending all of these forms and materials out to you guys through email, okay, because I'm not there in the group, in your WhatsApp group. I will be doing this through email. Okay, so let's look at the Runge Kutta method. Okay, it's called the Runge Kutta. It's not Runge Kutta. Okay, it's called Runge Kutta method. Now, the second order Runge Kutta method. Okay, so what do we do here? We're basically dividing the interval into 2 so that you get a better estimate of the slope. Like we said, we have as you make the interval smaller, you're going to get a better estimate. So what we're going to be doing here is we're going to divide the interval into 2. And we're going to be trying to find the estimate of the function, okay, or the slope. Okay, we're going to be estimating the slope. Function, slope, all are same. Okay, so you have to keep that in your head. The actual value of the function would be different from the function that you predict. Okay, but the function and the slope are quite the same. Okay. Now we can extrapolate this point halfway across the interval and then use the derivative at that particular point to extrapolate across the whole interval. So how does the formula look like for your Runge Kutta method? You have k. Okay, k, this particular value of k will be put into the y value. Okay, so this particular value of k that you calculate here, okay, will be put into this part. Okay, it will be put into this part. So you have yn plus k by 2 over here. Okay, and then you're doing it halfway across the interval. So you have delta x divided by 2. Okay, so halfway across the interval, delta x divided by 2. You will have to multiply this with your step size, delta x. Okay, so that's the only difference that you have here and your Runge Kutta method. Okay, we will explore this a little bit more. The reason why I'm giving you this formula is so that you can do the homework. Okay. Now, why do we have order of delta x power 3? Okay, in your Euler's method, what was the order of error that you had? What is the order of your truncation error that you had? Local truncation error, you had delta x squared. Okay. Now, when we're looking at second order Runge Kutta method, we're looking at second order. Okay, so your order of truncation error is going to be delta x power 3. If you're looking at the fourth order, it's going to be x power 5. So basically, the order of your error is going to be the order of your equation plus 1. Okay, so that's going to be the order of error that you have. Okay, so now you have this particular thing. Okay, and let's look at, okay, so one of the other things that tells you is that it has the same accuracy of the Taylor series. So if you do a Taylor series expansion for 2 variables, okay, so x and y, both, it's not a single variable Taylor's expansion, it's a multivariable Taylor's expansion. So if you try and expand it, if you try to compare the third term, let's say, So for second third, yeah, third term, then you end up getting x minus a whole cube, right? So you have x minus a whole cube f double prime, triple prime. So so if you do not have that particular a value, it's going to be of the order of x cube. Okay, so that's how that error comes up. Now what do we do here? We need to calculate the function twice for each step here. Okay, so in the previous one, you had to only calculate the function once for your Euler's technique. Here you have to calculate it twice. Okay, and there are several order Runge Kutta methods. You have third order, fourth order, and so on, goes on. But the fourth order is considered to be the best because of the computational limitations that you have and the amount of equations that you have to solve. So you have, for one iteration, you have to solve n number of equations, right? So here, this is considered to be ideal to do a lot of problems. So the fourth order is the most ideal, is what is considered typically. We will discuss about this later on. This is just to give you an idea of what the formula looks like. Okay, so we discussed about the accuracy, we discussed about the local accuracy. Now what do we have? We have K1, K2, K3, K4. Once you find out all these K1, K2, K3, K4s, you're going to be substituting it back into this solution, okay? Solution at a particular discretized point. And then you will be calculating. So this is how the formula is going to be given to you. Now, what I want you to do in your homework is you will take the same problem that I showed you, okay, your Newton's law of cooling, and you will not do it for Euler's method, but you will do it for the fourth order Runge Kutta method, and you will do it for the second order Runge Kutta method, okay? The reason why I'm asking you to do it yourself is because you get a practice of doing this, okay? Because this is something that is mentally intensive, okay? So like you have to sit down yourself and work with it. Okay, it's not that it's very hard to learn. It is very easy to learn. And because it is very easy, you really don't do it. Okay, you really don't do it. So you don't get the practice and then you end up making mistakes in your exam. Let's get some practice. Okay, so for practice, you will do this. I will send you another form for that. Okay, we will discuss about things later. Let's take one thing at a time right now. Okay. So yeah, this is the homework problem I told you. Take the same problem and do it for these two things. Okay, and I'll tell you how to submit your homework problems later on. Okay, so let's start off with this polling. Okay, so what is the first order Runge Kutta method called? Okay, so there's no such thing as the first order Runge Kutta method, Euler's method, Hume's method, Gauss-Legendre method. So let's start off with this poll. Okay, yeah. So let's start off with the fourth poll. Okay. Okay, submit your answers. We'll wait for a minute, just a minute, because we're at 10 now. And we started 10 minutes late. So, okay. Okay. 5 of you guys. Wow. Okay. Answers are interesting. Twenty more seconds to enter your answers. Ten more seconds to enter your answers. Okay, I'm stopping the polling now. Okay, so I'll share the results with you guys. Majority of you answered the correct answer. It's called Euler's method. Why? Because you're using the first order differential equation, and there's one slope that you're going to be evaluating. Now, there is no such thing as a first order RK method. No, all the methods are RK methods. Okay, all the methods are Runge Kutta methods. The first one is particularly called Euler's. Okay, so that's what we have. The other two answers, I don't even know why you've selected, because we haven't even discussed those things in our lectures. Okay, so okay, so that is done. We're done with our polling. Now let's go to, okay. So I'm going to give you an introduction of this this session, this particular thing. Okay, so equations of motion, your second order ODEs, and then we will discuss about this till later on. Okay, we're going to be using the Euler's method, the Runge Kutta method, second order and fourth order, and try to evaluate this. Okay, so let me just show you how this is, because we need to look at freely falling bodies, and Newton's laws of motion basically govern all kinds of classical motion, right? So we're going to be using that, and then we're going to be getting two first order differential equations. We're going to take a second order differential equation. Okay, so let me just write that down. You take a second order differential equation and you make that into two first order differential equations. And it's pretty simple. Okay, it's not very complicated as it sounds. First order differential equations. Okay, order. Okay, it's not very complicated as it sounds. It's quite simple and quite easy. You'll probably laugh. You'll be like, oh, we already know how to do this. Okay, so we know that the equations of motion of the object is governed by Newton's equations. Okay, in the one-dimensional case, we can define the instantaneous position y of t and the velocity v of t and acceleration a of t as an object using this. Okay, so how do you write your velocity? Dy by dt. How do you write your acceleration? Dv by dt. Okay, now the particle's motion, what is it basically defined by? What does your second Newton's law tell you? Okay, so you have d squared y by dt squared is equal to f of t divided by m. Okay, so that's a different way to write the, basically it's f is equal to m into a. I'm just writing it in terms of your second order derivative. Okay, now you want to be able to split them up into two first order differential equations. Why? Because I can solve first order differential equations using this Runge Kutta method, using your Euler's method easily. Okay, so I will split them up into two. That means you will have two solutions, okay, for this problem, to solve this problem. So the second order differential equation can be written as two first order differential equations. So you have dv by dt is equal to f of t divided by m, and dy by dt is equal to v of t. Okay, so to solve it, we can apply any of the methods that we discussed previously, and we are going to pick Euler's now. Okay, so you have, what is the solution over here? It's going to be v of n plus 1. This is basically your f of x comma y if it's dependent on two variables. Okay, so you have vn plus 1 is equal to vn plus, where did this constant come from? This constant came from the fact that this is a slope. Okay, so you have f of t divided by m. Okay, so you have dv divided by dt, which is basically your slope. So you have f of t divided by m, and then the discretized element that you have delta t. So you have discretized time, so you have time there. And what is f of t divided by m? Basically, it's your a of t. Okay, so that's your acceleration, right? So next, what do we have? We're going to look at the trajectory. Okay, so we have to look at the velocity. We have to look at the trajectory. So you have y of n plus 1 is equal to y of n plus v of n delta t. Okay, where a of n is equal to f of t divided by m. Okay, so you just have to substitute this in this first equation. Your a of n is equal to f of t divided by m. So you got your velocity, you got your trajectory. Okay, and how did you get that? You split the second order differential equation that you had before into two first order differential equations. So then you were able to use Euler's method more efficiently. Okay, so we've come to the end of this. Okay, I think I was able to do it perfectly within about an hour, less than an hour, including the polls and stuff like that. Okay,